Okay, so let's talk about limits. So to kind of introduce the concept of limits, let's look at this. What if we were interested in this function, right? So x squared plus x minus 2 all divided by x minus 1. And specifically, what if we wanted to know what is this function at x equals 1? Well, that's easy, right? Let's just plug in 1. So do substitution, and you'll notice you'll get a 0 over 0. And since there's a 0 in the denominator, this point is undefined, right? It doesn't exist. So here we have a function that we're interested in, and we're interested in a point that when we plug it in, it doesn't exist. So the kind of the point of this is that all? So do we just stop at, oh, well, it doesn't exist, so we're done? Well, unfortunately, there's a lot of wonderful things in mathematics, calculus being one of them, that's built on things or understanding what happens at places that don't exist, right? So we really, really want to kind of develop an idea that will help us figure out not that it doesn't exist at this point, but what happens around this point. That's what we want to do. All right. So here's the idea. Here's my function. If we did a graph, this actually graphs to be a nice straight line, and then at x equals 1, there's an open circle. Right. That's the point that doesn't exist. So let's do this. I want to know, since we already know that at 1 the function doesn't exist. Well, what would the behavior be around 1? So since we already know that at 1 it doesn't exist, the only thing we're left with is, well, what happens close to 1? What happens around 1? Well, let's look at x equals 1. Well, that's x equals 1. And so I did the colors here because there are two parts to this idea. One is, where do you want to look? And that's x equals 1 around it. And then the other is, well, what happens to the function? And the functions are y values, right? So the output, the behavior of f of x will be the output. So here's x equals 1. That's where I want to look. And then this will be around 1. So I don't want to look all over the place. I just want to look close to x equals 1 and see what's going on with the function. Mm-hmm. Well, I'm going to zoom in a little bit. You can tell right away if you just look inside the circle, the function acts linear, right? And in fact, around 1, right, it's going to act like a certain point. So let's see about this. Well, if I pick y's outside of this 1, so, if I picked an x over here, that would be this y value. If I picked an x here, that would be this y value. So around this open circle, these y's, right, on the left side act like 2.8, and on the right side, 3.2. Well, if I keep getting closer, then on the left side, the y looks like 2.9, the right side, y looks like 3.1. And if I keep getting closer, this y would be 2.99 and maybe 3.01. So as I get infinitely close, as I get closer and closer and closer, this function just acts like 3. So what we're saying is, yes, I know there's no y value at that point. But if we get really close, if we just look around 1 infinitesimally close, this function is going to act like 3. Okay, and that's the deal. So this behaves like 3 around x equals 1. All right. Okay, so that's the idea of limits. Limits are, what does the function behave like, right, when I look around very close around a point. All right. Okay, so that's the idea. So just limits represent the behavior of a function. And remember, the behavior of the function is the output of the function. That's the behavior we're talking about. And then near a particular input. So limits are all about, give me an input and I'll find you, right, what the behavior output or what the output behaves like. All right, that's our deal. All right, so we can determine limits or behaviors from graphs and tables. And we're going to do both here in a second. So let's start with the graph first. So I have a weird graph, a lot of discontinuities. I want to know the behavior of this function. So the functions, graphed in blue, near x equals -3 and 0 and 7. Well, let's go to x equals -3 first. So right there. I'm going to look around -3. So I want to go very close to 3. And then what does this look like? Well, as I come up here, it looks like the y values are going to approach -3. And as I come down here, it looks like the y values will approach -3. So it looks like this function behaves like -3 around x equals -3. All right. Okay, now how about 0? Well, here's x equals 0. Here are my two outputs at x equals 0, right? And now remember this, what it behaves like. So it looks like as I come in from the left, right, it behaves like y equals 0. And as I come in from the right, follow the graph, it behaves like 5. Right? Remember, it's okay that it doesn't equal anything up here because we're getting really, really close. So this graph, and you can even see that it's a straight line, it's linear, it points right to 5. So it's going to behave like 5. So at 0, right? So if we look around 0, this graph actually, this function actually behaves like 0 if I look left, and it behaves like 5 if I look right. Okay? All right, and then our last one about 7. Here's 7. So again, look around 7. So it looks like -2 the whole time here, -2 the whole time here. So it looks like this function acts like -2. There's just a hole here. So it means that the function behaves like -2 around x equals 7. All right. Okay, so again, you're looking at what the output behaves like really close to that input. All right, so you want to stop this and complete class or problem number 1. All right, so now let's do tables and graphs here. Or we did graphs, I'm sorry, let's do tables. So I want to know, what does the function behave like around x equals -3? Well, let's say here's a table. Well, here's around x equals -3. I have -4.5, -4. So this is coming in from the left. And then these numbers are bigger, so these are coming in from the right. And now I look at the y values. So as I come in from the left, it looks like I'm approaching -3.5. As I come in from the right, oops, I screwed that up. As I come in from the right, it looks like I'm approaching -2.5. All right. So there's a problem here. So when we look around the number, around -3, we need to be extremely close to -3. So these numbers are just way too far away from -3. All right. So this is misleading. It doesn't act like -3.5. It doesn't act like -2 because we're not close enough to this number to see what it really acts like. So that's the first tip. And I'll have some notes here in a second. So if you want to look at behavior around a number, you need to be very close to that number. And my nice rule of thumb here is I take the number and then I subtract off -0.001, -0.01, and 0.1. So I'm always, 3 decimals away, 2 decimals away, and then 1 decimal away. And then same thing, I'll add 0.001, 0.01, and then 0.1. So now if we have these numbers and we put it in our function, now we'll get these outputs. And now you can see from these outputs, since we're so close to this value, now it's really clear what the pattern is, right? So now you can see as I come in from the left, I approach -3. And then as I come in from the right, I approach -3. So this function actually acts like -3 at -3. Okay? All right, well, let's try another one. Oh, notes first, right? So again, when finding limits using tables, right, create a table with 7 spots in it, right? In the middle spot, you're going to put that x value, right? Whatever you're looking to be, whatever you're looking around, that'll go in the center. And then on the left side, just subtract 0.1, 0.001, and 0.00, or sorry, 0.1, 0.01, and 0.001. All right, and you want to put them in order, in descending order. And then from the right, you're going to add 0.1, 0.01, 0.001, and again, put it in ascending order. I think I said descending on the left. So it's always, you're going to go ascending order. So from left to right on a graph, they'll always be increasing, right, the x values. Okay, so let's do this. So right here, so let's say I have 0 as my point of interest. So here's my 7 spots. So 3 right, 3 left, put 0 in the center. And you can see from here, I subtracted off 0.001. Then I subtracted off 0.01 and then 0.1. Okay, and you can see these are increasing to 0. So these are coming in from the left. And then here from 0, I added 0.001, then I added 0.01 and 0.1. And you can see they're increasing. So as I come in this way, I'm actually approaching 0 from the right. Okay, and these are my values, my y values. So what's the behavior of the function around 0? Well, as I come in from the left, it looks like it's approaching 0. All right, that's what this pattern represents. As I come in from the right, it looks like I'm approaching 5. So this is what this pattern represents. So it looks like the behavior is, as I come in from the left, y's are 0. And as I come in from the right, the y will be 5. All right, let's do 7. So now again, notice what happens. 7, I subtracted off 0.001, then 0.01, then 0.1. And then I put it in ascending order. And I added 0.001, added 0.1, and added, or 0.01 and added 0.1. Okay. All right. So now as I come in from the left, all the y values are the same, so that's going to be a -2. As I approach 7 from the right, I'm also going to be a -2 because all these y values are the same. So this function acts like or this function around 7, right? X equals 7 acts like y equals -2. All right. Okay. So now here's the connection. So table, or from the graph, you could see visually what happened. The tables show me the exact same thing. So the last 3 examples we had in the tables was this graph. So you can see as I look in the table, I approach -3 from the left, and that's what's happening here. I'm coming up to -3, and then I'm coming down to -3 from the right, so here. So you can see the table will give me the exact same representation as the graph. You just have to start seeing the tables that way. All right, so now the next one. Looks like I'm coming up to 0, which is exactly what's happening here. I'm coming up to 0. This looks like I'm coming up to 5, which is exactly what's happening here, coming up to 5. So this table represents, right, that picture. And then lastly, it looks like as I come into 7, it's always -2, right, from the left. And as I come into 7 from the right, it's always -2 right here. 7 from the left, -2, 7 from the right, -2. So that's the table for this particular graph, right? This visual representation. All right. Okay. All right. So you want to stop this and complete classwork problem number 2. Okay. So now let's talk about limits. So we just did the concept of limits. The concept of a limit is, right, the behavior of the function around a certain input, an x value. So the notation for limits is this. All right. So it's LIM, and then there's this x arrow a, and then this function notation that equals L. Okay. So now what are these pieces? Right, first, let's go back. Yeah. So first, to read this, you would read this limit of f of x as x approaches a equals L. All right. So it's limit of the inside. And then you just breathe this off. So as x approaches a, and then the actual value it is, that's the actual limit. That's the behavior of the function at that x value. All right. Okay. So the pieces, the lim just is abbreviation for limit. X approaches a, that's the input. It's where you want to look. The f of x is just the function, right? So that's what you want to investigate, that function. And then L is actually the limit. It's the value. It's the behavior of that function, okay, or around that x point. All right. Okay, so I'm going to stop this and do classwork problem number 3. And now let's do some limits. So let's evaluate this limit. So again, it's a red limit of 3x minus 1 as x approaches 1. So I want to find the limit of 3x minus 1 as x approaches 1. And specifically, I'm going to do it with a graph and a table. And then the last one I'm going to show you, there's a little kind of trick to these first easy limits. So let's do a graph. Before we start though, right? So remember, what does this mean? It means I want to find the y value of this function around this point, right? So when I say behavior, remember, it's the output. So I'm going to find the y value of 3x minus 1. So if I were to graph it, here's graphing y equals 3x minus 1. Well, what do I want to do? I want to find the y value around x equals 1. So let's plot up x equals 1. This is where I want to look. So what's happening around x equals 1? Well, as I come in, it looks like I'm approaching y equals 2. As I come in here, I'm approaching y equals 2. So really close to x equals 1, we're going to become closer and closer to y equals 2. And so the behavior of this function around x equals 1 is 2. So we would say that the limit of 3x minus 1 as x approaches 1 equals 2. And what does this tell me? It tells me the y value of this function is 2 around x equals 1. All right, so y would approach 2 as x approaches 1. That's what that tells me. All right, let's try a table now. So we have our 1. So we're going to put that right in the center. Now let's do our add and subtract our bits. So let's subtract off 0.001 to get 0.99. Let's subtract off 0.01 to get 0.99. And let's subtract off 0.1 to get 0.9. Okay, and you can see these numbers are increasing up to 1. So this is coming in from the left. Okay, from the right, just add 0.001, add 0.01 and 0.1. And so now you can see these are still increasing. So as I come in this way, this is approaching 1 from the right. Okay, so this comes up to 1, and this comes down to 1. All right, now plug them in. So 0.9, plug into this 3x minus 1, 0.99, plug into 3x minus 1, and do it for all of them. Okay, if you do that, you'll get these values. And now look at your patterns. What happens is I come up to 1. Well, when I said 1, x equals 1, well, as I come up to x equals 1, the y's, it looks like, will come up to 2. Right? And if you can't see it, then get closer. Maybe do 0.9999. Right? What happens is I come down to x equals 1. Well, it looks like the y values also are approaching 2. Right? So since the behavior left and right matches up, it looks like they both, y values approach 2, then the limit of this function around x equals 1, right, or as x approaches 1, is 2. All right? Okay, the last thing I'm just going to show you real fast. There's nothing weird about these functions, right? So in the very beginning of this video, I showed you a rational where there was a 0 in the denominator. When you start learning limits, we do these easy functions that are just, you can plug them in. Well, notice that if I did f of x is 3x minus 1 and evaluated it at 1, so at f of 1, y is 2. Well, if y is 2 at 1, and this is continuous, right, it's just a linear equation, then the actual behavior of the function has to be 2, right? So sometimes you're able to plug in the x value, find your y value, and that's the limit. Like I said, those are the easy ones because that's what happens when you start learning these things. All right? Okay, so 3 ways you can find limits. Tables always work. Graphs always work. Sometimes graphs are hard. You can't be exact. And then this evaluation part, this doesn't always work. It has to be continuous for this to work. All right? Okay, that's actually the end of the video. So stop it and do classwork problem 4 and 5.